Hello everyone, welcome back all of you, and in this session we are going to talk about Cauchy Euler differential equations, because in the case of higher order linear differential equations, as of now we were talking about the differential equation whose coefficients are constants, like the coefficients of a differential equation. We had assumed that they are going to be k1, k2, k3, and we assume them as constant. But in the case of Cauchy Euler differential equations, instead of having constant coefficients, we are going to have the terms of x, but in them also we are going to talk about only terms of x, but they are going to have the same degree as of the differential. Like if it is d2 by dx2, we are going to have x square term. If it is dy by dx, we are going to have x term in the multiplication. So this kind of format we call it as Cauchy Euler differential equations, because even in the non-constant coefficient differential equation we have multiple varieties, but from gate point of view we have to discuss this only in the case of non-constant coefficient. So what we have to do, we have to keep in mind that we have to make use of little substitution, that x we are going to substitute as e power z, and wherever we find x into dy by dx, so x into dy by dx we are going to put as dy, and wherever we find x2 dy by dx2 we are going to put it as d into d minus 1 y. And in the previous session capital D was nothing but d upon dy, but in this case it is going to be d upon dz, because we made the substitution x as e power z. So I have taken two examples, one I have taken from homogeneous part and another one I have taken from non-homogeneous part, and we are going to write the complete solution, because the complete solution is nothing but complementary function plus particular integral. But in the case of homogeneous we are not going to have the particular integral, we are going to have only complementary functions, because right hand side it is 0, so there is no particular integral part in that. But in the case of non-homogeneous linear differential equation we are going to have particular integral also. So by combining both of them we are going to write the complete solution. So let us discuss the problem number 1. So this is nothing but like x2 into dy by dx2, we have to put d into d minus 1 y, and minus 4, and x into dy by dx we have to put as dy, and plus 6y is equal to 0. So by simplifying it, d into d minus 1 minus 4d plus 6, and take the y term out. So we are going to get it as d square minus d minus 4d plus 6. So this is nothing but d square minus 5d plus 6, d square minus 5d plus 6 into y is equal to 0. And why I am calling it as homogeneous, because we have equation something like f of d into y is equal to 0 form. So how we are going to write the general solution, we have to write the auxiliary equation f of d is equal to 0 and calculate the root. So d square minus 5d plus 6 is equal to 0, and the roots are nothing but 2 and 3. And also I said how to get that, I told about the method of factorization, right? So make the midterm as summation of two numbers, so like minus 2d and minus 3d. So this is nothing but minus 5d, and this should be multiplication of these numbers, because x square minus alpha plus beta into x plus alpha beta, this is nothing but and standard quadratic function whose roots are alpha and beta, and this also I made use of at one place also. So this is nothing but x square minus alpha plus beta x plus alpha beta. So if the roots are 2 and 3, so this is nothing but x square minus 2 plus 3 minus 5x, and 2 into 3 6. So with this standard format only we call it as factorization of getting the factor of quadratic equation. So we have the root as 2 and 3, so we have real roots, so we are going to write the general solution, the complementary function, as c1 e power ax plus c2 e power bx. So this is going to be our answer, but we have to keep in mind this is not at all x, because capital D here is d by dz, it's not d by dx. So this is going to be e power 2z and e power 3z. This we have to be very careful, because we have put it e power z as x. So now we have to substitute x back, and we are going to get c1 x square plus c2 x cube, because if x is e power z, x square is nothing but e power 2z, and x cube is nothing but e power 3z. So this is the complementary function, and this is also going to be the complete solution, because y is equal to yc plus yp, but in the case of homogeneous linear differential equation we don't have yp part, so complete solution will be yc only. So that's how you have to deal with the homogeneous linear differential equations. And now let us talk about the problem number 2, which is non-homogeneous linear differential equation. So again, make the substitution x2 into dy by dx2 as d into d minus 1 y, and minus 2 x dy by dx as dy plus 2y, and is equal to 4, because this 4 you will have to take outside, because all the time you have to keep in mind f of d into y should be capital X. So in the left hand side only terms having the multiplication of y only we have to take care. Don't confuse yourself that if it is right hand side 0, this is homogeneous one. No, you have to take the equation something like f of d into y is equal to capital X. If in this format capital X is 0, then you have to call it as homogeneous one. So this is not homogeneous, this is non-homogeneous linear differential equation. So d square minus d minus 2d plus 2, and by I have taken common, so this is nothing but d square minus 3d plus 2 into y is equal to 4. So we can see clearly this is of form f of d into y is equal to capital X, and capital X is nothing but a constant. So we are going to fall under the case number 1, either it is e power ax plus b or constant, right? So in the case of non-homogeneous linear differential equation, writing the particular integral part, we have seen it very clearly over there. So yeah, so now what we have to do, first we have to treat is like homogeneous linear differential equation, d square minus 3d plus 2 into y is equal to 0, and write the complementary function like the general solution of homogeneous linear differential equation. So roots of this particular equations are nothing but 1 and 2, because minus 1 and minus 2 is like minus 3d, or if I compare it with the standard form, as I said, x square minus alpha plus beta x plus alpha beta. So alpha plus beta is nothing but 1 plus 2 is 3, so 3, and 1 into 2 is nothing but 2. So roots are 1 and 2. Again the distinct real root we are getting, so we are going to write the complementary function as c1 e power z plus c2 e power 2z. And also this you have to keep in mind, these are not x, these are z, because capital D is nothing but d by dz. And now you will have to substitute e power z back as x. So this is nothing but c1 x plus c2 x square. So this is the complementary function, the general solution of homogeneous linear differential equation. And now you will have to calculate the particular integral part also, because this is non-homogeneous linear differential equation. So yp you are going to write as 4 upon f of d is nothing but d square minus 3d plus 2. And if you compare it with e power ax plus b case, a is equal to 0, b is equal to 0, and what you have to do, replace d by a. So a is nothing but 0, so you have to do yp is equal to 4 upon f of 0, right? So 4 upon replace 0 here, this is nothing but 0 plus 0 plus 2, so this is nothing but 2. So the particular integral part is going to come out as 2. So we have the complete solution, y is equal to yc plus yp, and yc is nothing but c1x plus c2x square, and yp is nothing but 2. So this is going to be a complete solution. So that's how you have to deal with the Cauchy's and Cauchy's Euler differential equation. And you have to keep in mind that Cauchy's Euler differential equations are nothing but the multiplication terms, like the non-constant terms are going to be in terms of x, but they are of same order of differential. Like if it is dy by dx, we have x in multiplication. If it is d2 by dx2, we have x square in multiplication, because then only we will be able to do the substitution x into dy by dx as dy, and x square d2 by dx2 as d into d minus 1 y. If it is of third order, so x3 dy by d3 y by dx3 we will write as d into d minus 1 into d minus 2 y. But up to third order they are not going to go, so up to second order you have to be very careful. So that's all for this particular session. If you have any doubt, you are free to ask in the comment section. Thank you.